Okay, here we go. Now we're going to talk about PLC inputs and outputs and how the PLC processes its information, which we call the order of operation. So we have some objectives in this lesson. We want to list the two basic types of PLC inputs. We want to define what a discrete input is, and we want to be able to define what an analog input is and be able to differentiate between those two. And we want to be able to explain the order of operation, which is basically explaining how the PLC that we're using in class is going to function each cycle. Okay, so let's talk about some PLC I/O types. Discrete inputs, I have some examples here, and analog inputs, and I'll have some examples of those as well. But those are the two types. There is only those two types of inputs and outputs we have in any control system. So let's look at a discrete input. A definition: a discrete input is a binary input that has two distinct states. So binary, like bicentennial or biannual, that means twice, or has two options. Just like a light switch has only two options, it has two states. It's either on or it's off. Our motor that we've been controlling is either running or it's not running. You could say it has two directions. It's either forward or reverse. It has no other options. Those are a two-state inputs. And that is what we term a discrete input. It has two discrete states to it. So let's give some examples of those. On and off. So we just have simple switches for lights that are on or off. But another device could be something that's either open or closed, not something that has a variance between open and closed. It just has those two states. So these are two examples here of a pipe that would have a valve in it. The one to the left is showing that there is water flowing through there because the valve is open. There is no obstruction and water is allowed to flow. The valve to the right has an obstruction, so there's water on the left-hand side, which is the blue color, and there is no water on the right-hand side because the valve is closed. It has two states, open or closed. Made or not made, we talked about this a little bit in manual motor controls. Our relay to the left is made, meaning the energized state of the electromagnet is pulling against that spring and closing the normally open set of contacts, making those contacts made. Where not made is on the right-hand side, meaning my electromagnet is not energized, it's not magnetic, and it's not pulling against that spring, so my contacts are in their shelf state or normal state. Running or not running, so this is just a little animation that shows a pump that is spinning to the left, meaning that it is running and pumping water or whatever the medium is, and to the right it is not running. Quite often we use green, meaning something is energized, and red as de-energized, so that's why the X is red and not spinning, showing that the motor is not running. And some other examples: enabled and disabled, whether we have a high level or the level is okay, those are only two states, and whether something is in alarm or the alarm is cleared, those are another options for discrete inputs that have two distinct states. Now, analog input is juxtaposed to that. It is going to have a myriad of states. It's going to have more than two states. It has a numeric input that has some sort of range of value spanning from some low value of 0 up to the maximum that it could represent, or 100% of its scale. Here are some examples. The level in a tank. The level in a tank could be anywhere from empty or 0 to 100%, which would be 100% full. You could quantify that in the amount of gallons. that is in the tank. So it could go from 0 to 12,000 gallons in the tank. So there's our symbol of a process tank that we learned about in the last unit. And I'm showing a little sight glass right there in the middle. And that tank is right in the middle. So it's maybe a little less than 50%. So a low-level switch or a high-level switch, neither one would be active because we're in the middle. And but we can also quantify how much water is in the tank. Where if we just had a low-level switch or a high-level switch, we wouldn't know how much water is in the tank. We would just know that we're not an alarm in either one of those two states. The temperature in a room from freezing all the way up to boiling. If we're talking about maybe the temperature in this tank of the water that's in that tank. And there again, we have just a symbol of a thermostat or a thermometer to show that that is a varying state that we want to be able to measure. So then we can control maybe the temperature in a room or something like that. Pressure, that's just a simple pressure gauge. That one happens to be for the HVAC industry, where you would measure the pressure inside a air conditioning system. So discrete states are either have two distinct states, on or off, open, closed, where analog has a range from 0 to 100% of scale. So those are our two different types of inputs. So let's look at our Micrologix PLC, the one that we're going to be using this semester, and its inputs and outputs. Its inputs are going to be in the top row of our controller when it's installed in our panel. And then inside the controller, we're going to have ladder logic. And I'm showing kind of a very simplified depiction of ladder logic there. And then the outputs are going to be on the bottom. So inputs come in on the top, and then the program's inside, and outputs go out at the bottom there. Okay, so let's talk about the operation of the PLC. The very first thing that it's going to do is it's going to read each input channel starting at the very first input channel. That is I/0. That's not the letter O, it's I/0, which means input 0. We're going to have a lesson next on addressing, but PLCs are what we call zero indexed, meaning when you start counting, you count from 0, then you go 1, 2, 3, 4, 5. So as I earlier stated in the previous video, we have 10 inputs on this PLC. They're going to start at 0 and go through 9. Okay, so that's something for a student to get used to, is when we normally count in the world, we start counting 1, 2, 3, 4, 5. Well, we're actually going to be counting starting at 0, 1, 2, 3, 4. And that's going to make sense when we study binary number systems in a future lesson. Okay, so here we're looking at address I/0, which the bubble there is pointing at that particular input, and it's going to read whether it has 24 volts present, because remember from the previous video, our particular model, all the inputs are going to be 24 volts DC. So we're looking for either 24 volts or 0 volts at that channel. Okay? Because remember, a discrete input can only have two states. And our two states on all of our inputs are going to be 0 volts or 24 volts. If 24 volts is present, the channel's bit is set to 1 in the input word. So I'm using a new term there, the term bit. And bit is just a number. It has one position, and in this case it's a discrete bit, which means it has only two states, and its two states are either 0 or 1. Okay, so that is kind of our definition of a bit. We're gonna, when we study binary numbers, we're gonna get into those terms a little bit more. But that channel's information, you could look at it that way. The channel's information is going to be set to 1 in an input word, and we're gonna look at what the input word is in just a minute here. If it is 0 volts present, then a 0 will be set to that input word. Okay, so remember, a discrete input only has 2 states. In our case, the 2 states are going to be 24 volts or 0 volts. Those are the only 2 options. We couldn't have 12 volts coming in there. It has to be 0 volts or 24 volts. Okay. Now, I've got the cart in front of the horse here just a little bit. We haven't gotten into the programming software at all. We're just kind of learning high-level concepts, and this is all going to be clear in a future lesson when we start talking about the actual software and the input tables and those sorts of things. This is a snippet out of the program that we're going to use to program this. But what I want to show you at a high level is that piece of information that we just determined, whether it's a 1 or a 0, is going to get stored somewhere. So that's all we're really trying to conceptualize here, is we're going to store that somewhere, and we're going to store it in a word. A word is a collection of information, in our case discrete bits or discrete 1s and 0s, and there's going to be a specific number of them, and the number is going to make sense in a future lesson. And we're going to gather those together, that collection of those numbers together, and we're going to compact them into a word. And then that's kind of a real easy way for us to port around that information. So you could think of this as how we purchase eggs. We purchase eggs, not one egg at a time. We go and we buy a carton of eggs, and a carton of eggs has a specific number, 12, in the carton. Well, a word is a specific number of bits. In our case, it's going to be 16. 16 of those together, and then we can transport those 16 pieces of information and move them around much easier than transporting 1 bit here and 1 bit there. Okay, so it's kind of a way of compartmentalizing things and being able to move them around together uniformly. Okay, so that's our input word, and our bit is going to go in this location right here. It is a bit 0, I/0, and so it's going to go in a specific location in that word. And if we start at the rightmost number, that's going to be the 0 place. And then as we move to the left, our bit location is going to move up by 1. So it'll go 1, 2, 3, 4, 5, all the way up to 15. Remember, I said we're going to compartmentalize this in groups of 16, but we are 0 indexed. So we're going to start at 0, and we're going to move to the left and increment up by 1, so it'll be 0 through 15. Okay, we're going to have a whole lesson on addressing, so we're just trying to understand at a high level these concepts. Okay. Now, we've only read one channel so far. The process that we're going to go through is then we're just going to move over 1 to the right on the PLC, and that would be I/1, and it'll get stored 1 to the left on our input word. Okay, we're gonna look at that here in just a minute. So after we scan all the inputs, in our case we only have 10, so we're just going to go through those first 10, and we're going to store them in that first word in the input file. Now we're going to execute our program that we have inside the PLC. Inside our PLC, we have a program that has one whole line in it, and that line has 2 instructions. So that we're going to evaluate that one line in our simple program here, and we're going to show you the steps on how we're going to evaluate that. Okay. The rung, we're gonna start at 0, rung 0. These numbers out to the left-hand side in the upper right-hand corner there are showing that the rung number And again, we're not starting at rung 1 like we did when we did our hand drawings for manual motor controls. Everything in the PLC is going to start counting at 0 and then go up. So our rung 0 is the first one that's going to be evaluated, and we're going to evaluate from left to right. So even though those look like a set of contacts and an output, those are actually instructions. We're actually going to talk about instructions in the next lesson as well. But what we're doing is we're just evaluating that rung 0 from left to right, and we're going to do that for each rung in the program. So it would go to rung 0 and evaluate from left to right all of the instructions. Then it would go to rung 1, evaluate left to right, and if there were a rung 2 and a rung 3 and a rung 4, it would evaluate all of those in order. And it knows when it is finished with evaluating the program when it reaches this end statement. So you can see the end statement in the upper right-hand portion of the screen, and it has kind of a black box around it. That lets the program know that we have reached the end of the instructions. And then the cycle will start again at rung 0 when we get to that part of the scan sequence. But we're still at step 2 of a 3-step process right now. Okay. This scan sequence happens very quickly. In our purposes for the small programs that we're going to be writing, it's going to be happening about 1,000 to 1,500 times per second. That's how fast we're going to be executing. Now, you think that's really fast. When we were in manual motor control, the electricity that was running through the lines is basically traveling at the speed of light, which is faster than 1,000 to 15 times per second. So PLCs are extremely fast, but they're still not as fast as the manual motor control wiring that we did prior. And the only operation that the execution of this ladder logic performs is reading from that table that I showed you prior, and then it is writing to the output table. It never reads from the actual field or the actual screw terminals that are on either the top, or writes to the screw terminals that are on the bottom of the PLC. It's just doing it within the tables inside the PLC. Then when we get to the next step, then we're going to take all the information that's in those tables and write it out to the outputs. Okay. So let's look at the rung execution here just a little bit closer. So the rung 0 is evaluated first. We're going to go to this instruction right here. And that instruction is going to, and notice I'm using the term instruction. I'm not saying that those are normally open set of contacts. They're not an open set of contacts. They could be a limit switch. They could be a push button. They could be contacts on a relay. We're going to talk more about instructions in the next lesson. But right now, just know that that is an instruction. And instructions have certain functions that they perform. And we're going to talk about that in the next lesson. So when I reach that, all that instruction is trying to do is figure out whether the address that is tied to that instruction is going to pass its test. So every instruction is a test. Okay? And the test is simple. It's either testing for a 1 or it's testing for a 0. That's as complicated as it gets. So this instruction here is actually testing for a 1. If it finds a 1 in the input table, it is going to evaluate to true. It's going to pass the test. And when it passes the test, inside a running program, it will highlight itself green. Now that doesn't mean that it's, quote, energized like electrically. What it means is it's logically true. And when it is logically true, then the logical continuity, or the logical, you can think of logically as electricity. Logically, it's passing on that true down the line. Now, in this particular case, there is only one other instruction, and that is an output instruction. If you notice, that instruction almost looks like the symbol for a coil, and that's on purpose. And that output instruction has an address associated with it that has an O in front of it, meaning that's an output. So we're reading an input and we're writing it to an output in this instruction. But we're actually reading an input bit from the input table, and we're writing to an output bit in the output table. We're actually not physically writing all the way to the output. Okay. Its instruction, the one that looks like a normally open set of contacts on a relay, tests the address, and we will have more on the instructions later. The result of this test is going to either be true or false, and a true evaluation will highlight our instruction green. Okay. Now, after all the instructions of a rung are evaluated, the result of the entire rung will either be true or false. Okay. Every rung must have some sort of execution or output instruction associated with it. If not, then the rung doesn't need to exist. If we're not driving some sort of conclusion, because remember, we're just basically asking questions to make a decision. And at the end of all the questions that we ask, we have to come up with some sort of conclusion. And the conclusion is an output. Now we're going to learn this more in the future, but the output could either be just internal, could be something that we're storing away a decision for a later decision to be made, or we could actually be writing to the output. But either way, we're going to use an output instruction for that. The rung 000 has one instruction before its output instruction, and since that instruction is evaluating to true, the output in the output table will be written to a 1. Okay? So again, we're not writing directly to the channel, we're writing to the table. And it's going to make sense here in just a minute when I show you the third step of what happens. So just to review, the first step is we went and we read all of the input channels and we just stored them in that input table. And you can think of those as just little locators in a spreadsheet. And then when we're going through and we're executing this program, when we're executing the program, we are looking at that spreadsheet and we're pulling out those pieces of information, and we're going to say, hey, was that channel on or off? And then we can actually test it to see whether it was off or on using different types of instructions. And based on those decisions, then we can write to output instructions. And when we're in this execution process, when we write to an output instruction, we set an output instruction true. We then write to an output table. Output table would be like another sheet in a spreadsheet that we're saving up our decisions of what we want the outputs to do. We haven't changed any of the outputs yet. We're just saving all of that information in a specific location in a spreadsheet. You can think about it that way. And a true result will highlight green for that output instruction. So in this case, we only had one test instruction in the 000 rung, and it evaluated to true. That's why it's highlighted green. And because it's highlighted green, my output instruction highlighted green, meaning that I'm going to set a 1 into the output table. Now we've gone through our entire program of one whole line, and we're done with that. So now all we need to do is take our output table spreadsheet that we have, and we're going to write those values straight to the output channels. Okay, so once all of those rungs have been evaluated, again, our program was one rung, and the outputs are written into those output locations in our spreadsheet. Now we're going to take them out of that spreadsheet. We're going to write them in order, starting with output 0. In our case, we only have 6 outputs, 0 through 5. We're going to write output 0 first, then output 1 next, then output 2 next, output 3 next, all the way up to 5. Okay. And so in this case, I only had one output in my program, and my output word, if you notice, this looks almost identical to the input word. The only thing that's changed is instead of an I in front of my my output word there, I have an O. And the output, since it's 1 in the table, we are going to put a write that channel to a 1. And the next slide is going to show us internally what's actually physically going to happen inside the PLC there. Okay, so we're going to read that value and we're going to write that output to that channel. Now what actually physically is happening is there's a set of contacts in there that's closing, but we're going to see that here in the next slide. Oh, I guess I have another presentation. So let's review, and I'll show you in the next one what is physically happening here with the inputs and the outputs. So let's list the 2 basic types of PLC inputs. Okay, we had one type that had 2 states. It could either be on or off, open, closed, running, not running, alarm, or clear. That is called a discrete input. And then we had another type that was a varying range of states between being at 0% of scale up to 100% of scale. And a level of a tank is a very good explanation. If the tank is completely empty, it has 0 level. If the tank is completely full, it has 100% level. But using different types of instruments to measure that, we could actually be sending signals anywhere between 0 and 100% that shows the actual level in the tank. If you want to learn more about that, sign up for CST. So let's define that discrete input. A discrete input is something that only has 2 states, on or off, open, close, running or not running. And an analog input, we just talked about that. It has a myriad of states between 0 and 100%. And we could tie engineering units to those. So not everything is measured in 0 to 100%. I can't tell you the temperature in the room is at 50% because we need to quantify that in some way. So we can tie engineering units to 0%. In the case of water, 0% would be 32 degrees because it's no longer water below 32 degrees. And we could set 100% at 212 degrees because once it reaches 212 degrees Fahrenheit, it's no longer water as well. It becomes a gas. So that for water would be our temperature range if we wanted to be at the outer bounds of that. And we could set that for a lot of different things. Explain the order of operation. First thing we're going to do, we're going to go and read all of our input channels. So in our case, with our little compact PLC, we have a grand total of 10 inputs. So we're going to go through starting at I/0, and we're going to read that input. If it has 24 volts, we're going to put a 1 in our input spreadsheet, our input table. And if it has 0 volts, we're going to put a 0 in that location. We're going to move on down the line, and each input channel has a specific location in our little input table, our little input spreadsheet that we're we're going to store that information. We're going to do that so the next step, when we get to evaluating our program, we've already got all of our inputs read. And then we're going to use the input information that we stored in my little table to determine with test instructions what we want to do with the information that is in that table. And so we're going to be learning about instructions, but our instructions will evaluate to some sort of whether our rung is going to be either the result of the entire rung is going to be true, or the result of the entire rung is going to be false. And then we're going to write that to some output. Every rung has to have an output, and an output instruction is what is going to write to an output table. It's I can't say it's the only way to write to the output table, but inside the PLC, it's the only way to write to the output table. There's other ways with computer programming outside of PLCs to be able to do that, but that's beyond the scope of what we're doing. Okay, so we are going to write to our output table from our program execution, but we're not writing to the output channel, just the table. And then the third step, step 3, is we're going to take all of the information that we stored in that output table and we're going to write it to our output channels. And we're going to start with output 0, then we're going to write output 1 on down the line to output 5. Okay, so that is again an overview of what internally happens inside the PLC. We call this order of operations. So just so we understand how the PLC operates is going to help us understand how to troubleshoot our PLC programs. If we get something out of order inside the program, it's really going to cause problems. And sometimes all we have to do is change the order in which our program is written, and it's going to solve a lot of troubleshooting problems that we can come up with. So hope that helps. We will see you in the next video.